This is an imperfect reading of Mycelium Running, How Mushrooms Can Help Save the World, written by Paul Stamets. Forward. Mushrooms, ignored by many, reviled by some, may turn out to be important keys to both human health and planetary health. Their indispensable role in recycling organic matter, especially in forests, has long been known. But how many people realize that trees and other green plants could not grow and reach maturity without symbiotic associations with mushrooms, at least with mycelium, the network of fungal threads in soil that acts in interfaces between plant roots and nutrients? A mushroom is the reproductive structure or fruiting body of mycelium. Mycelium runs through our world, performing many other feats as well, but it is hidden and inconspicuous, a strange life form that has not attracted the same scientific attention as microorganisms or plants or animals. Even conventional mycologists hardly recognize its larger implications and possibilities. Paul Stamets has never been a conventional thinker. I've known him for 25 years, and during that time, I've been repeatedly impressed by his insights into the interdependence of human beings and nature, his enthusiasm for harnessing and directing biological energies toward higher purpose, and his talent for thinking in novel and inventive ways. He has always looked at mushrooms from unique perspectives, and as a result has made remarkable discoveries about them. When we first met, I was questioning why Western medicine had never looked to mushrooms as sources of new therapeutic agents, given their prominence in the traditional pharmacopoeias of China, Japan, and Korea. Paul took that question and ran with it, focusing on the natural competition that exists in soil between mycelium and bacteria. Fungi have evolved novel chemical defenses, a range of antibiotics that are often active against not only bacteria but also viruses and other infectious agents that cause disease in humans. One of the big ideas in this book is that fungi, especially fungi from old-growth forests, may be sources of new medicines that are active against a range of germs, including HIV and AIDS, and the causative agents of smallpox and anthrax, potential bioterrorist threats. Another of Paul's big ideas is that mycelium can be selected and trained to break down toxic waste, reducing it to harmless metabolites. He calls this strategy mycoremediation and has demonstrated its practicality in cleaning up oil spills. He suggests that our mushroom allies may even be able to detoxify chemical warfare agents. This is one facet of a larger strategy that Paul calls mycorestoration, the use of fungi to improve the health of the environment by filtering water, helping trees grow into forests and plants to grow into gardens, and by controlling insect pests. The last possibility is especially noteworthy because it has the potential to neutralize pests like termites and fire ants by means that are completely non-toxic to human beings. Paul Stamets holds a number of patents in these areas, and I look forward to seeing his inventions put to use. As a physician, as a practitioner of integrative medicine, I find this book exciting and optimistic because it suggests new, non-harmful possibilities for solving serious problems that affect our health and the health of our environment. Paul Stamets has come up with those possibilities by observing an area of the natural world most of us have ignored. He has directed his attention to mushrooms and mycelium and has used his unique intelligence and intuition to make discoveries of great practical import. And I think you will find it hard not to share the enthusiasm and passion he brings to these pages. Court Island, British Columbia, June 2005. Andrew Weil, MD. Preface. For 30 years, I have engaged fungi, or perhaps they have engaged me, in a mission to promote the benefits of mushrooms. My previous books, Growing Gourmet and Medicinal Mushrooms, 2000, and The Mushroom Cultivator, co-authored with Jeff Chilton, 1983, delve into the methods of cultivating mushrooms. This new book is designed to show readers how to grow mushrooms in gardens, yards, and woods for the purpose of reaping both personal and planetary rewards. As you will discover, mushrooms help us reconnect to nature in profound ways. Mushrooms, mysterious and once feared, can be powerful allies for protecting the planet from the ecological injury we inflict. More specifically, this book focuses on healing the planet using mycelial membranes, also known as mycelium, a fungal network of thread-like cells. It is a mycological manual for rescuing ecosystems. Engaging mycelium for healing habitats is what I call mycorestoration. The umbrella concept of mycorestoration includes the selective use of fungi for mycofiltration, mycoforestry, mycoremediation, and mycopesticides. Mycofiltration uses mycelium to catch and reduce silt and catch upstream contaminants. Mycoforestry uses mycelium and mushrooms to enhance forest health. Mycoremediation neutralizes toxins. Mycopesticides refers to the use of fungi to help influence and control pest problems. This quartet of strategies can be used to improve soil health, support diverse food chains, and increase sustainability in the biosphere. This book is written for a readership as diverse as the fungal community, for readers devoted to recycling, organic cultivation, habitat restoration, or applied mycology. I hope this book will be as useful as it is revolutionary. If you are a landscaper, bioremediator, eco-forester, sustainable village planner, physician, scientist, futurist, or anyone who is passionately be-mushroomed, I hope this book enriches your life and that you will pass on the love of mushrooms to future generations. And even if you have never walked through an old-growth forest, cultured fungus in a petri dish, relished a fresh-picked matsutake grilled over an open fire, or taken a mushroom-based medicine, I hope you will find this book and my pragmatic environmental philosophy described herein informative and inspiring. I contend that the planet's health actually depends on our respect for fungi. This book will show you how you can save the world using mushrooms. Part 1. The Mycelial Mind. There are more species of fungi, bacteria, and protozoa in a single scoop of soil than there are species of plants and vertebrate animals in all of North America. And of these, fungi are the grand recyclers of our planet, the mycomagicians disassembling large organic molecules into simpler forms, which in turn nourish other members of the ecological community. Fungi are the interface organisms between life and death. Look under any log lying on the ground, and you'll see fuzzy, cobweb-like growths called mycelium, a fine web of cells which, in one phase of its life cycle, fruits mushrooms. This fine web of cells courses through virtually all habitats, like mycelial tsunamis, unlocking nutrient sources stored in plants and other organisms, building soils. The activities of mycelium help heal and steer ecosystems on their evolutionary path, cycling nutrients through the food chain. As land masses and mountain ranges form, successive generations of plants and animals are born, live, and die. And fungi are a keystone species that create ever-thickening layers of soil, which allow future plant and animal generations to flourish. Without fungi, all ecosystems would fail. With each footstep on a lawn, field, or forest floor, we walk upon these vast sentient cellular membranes. Fine cottony tufts of mycelium channel nutrients from great distances to form fast-growing mushrooms. Mycelium, constantly on the move, can travel across landscapes up to several inches a day to weave a living network over the land. But mycelium benefits our environment far beyond simply producing mushrooms for our consumption. Humans collaborate with these cellular networks using fungi, specifically using mushroom mycelium as spawn for both short and long-term benefits. Mushroom spawn lets us recycle garden waste, wood, and yard debris, thereby creating mycological membranes that heal habitats suffering from poor nutrition, stress, and toxic waste. In this sense, mushrooms emerge as environmental guardians in a time critical to our mutual evolutionary survival. I believe random selection is no longer the dominant force of human evolution. Our political, economic, and biotechnological policies may determine our future, for better or for worse. Some forecasts claim that half of the current species could disappear in the next 100 years if the current trends continue. A "What If" Pentagon report issued in October 2023 titled "An Abrupt Climate Change Scenario and Its Implications for the United National Security" by Schwartz and Randall 2003 hypothesizes that a more dire and imminent collapse of our biosphere may occur as climates radically destabilize as a result of pollution and global warming. I wonder what would happen if there were a united organization of organisms, UOO, pronounced uh-oh, where each species gets one vote. Would we be voted off the planet? The answer is pretty clear. When we irresponsibly exploit the earth, disease, famine, and ecological collapse result. We face the possibility of being rejected by the biosphere as a virulent organism. But if we act as a responsible species, nature will not evict us. Our fungal friends equip us with the tools to act responsibly and repair our shared environment, leading the way to habitat recovery. So knowing how to work with fungi by custom pairing fungal species with plant communities is critical for our survival. The 21st century may be remembered as the biotech age, when these kinds of mycotechnologies play a prominent and increasing role in the strengthening of habitat health. Chapter 1: Mycelium as Nature's Internet. I believe that mycelium is the neurological network of nature. Interlacing mosaics of mycelium infuse habitats with information-sharing membranes. These membranes are aware, react to change, and collectively have the long-term health of the host environment in mind. The mycelium stays in constant molecular communication with its environment, devising diverse enzymatic and chemical responses to complex challenges. These networks not only survive, but sometimes expand to thousands of acres in size, achieving the greatest mass of any individual organism on this planet. That mycelia can spread enormous cellular mats across thousands of acres is a testimonial to a successful and versatile evolutionary strategy. The history of fungal networks. Animals are more closely related to fungi than to any other kingdom. More than 600 million years ago, we shared a common ancestry. Fungi evolved a means of externally digesting food by secreting acids and enzymes into their immediate environs and then absorbing nutrients using net-like cell chains. Fungi marched onto the land more than 1 billion years ago. Many fungi partnered with plants, which largely lacked these digestive juices. Mycologists believe that this alliance allowed plants to inhabit land around 700 million years ago. Many millions of years later, one evolutionary branch of fungi led to the development of animals. The branch of fungi leading to animals evolved to capture nutrients by surrounding their food with cellular sacs, essentially primitive stomachs. As species emerged from aquatic habitats, organisms adapted means to prevent moisture loss. In terrestrial creatures, skin composed of many layers of cells emerged as a barrier against infection. Taking a different evolutionary path, the mycelium retained its net-like form of interweaving chains of cells and went underground, forming a vast food web upon which life flourished. About 250 million years ago, at the boundary of the Permian and the Triassic periods, a catastrophe wiped out 90% of the Earth's species when, according to some scientists, a meteorite struck. Tidal waves, lava flows, hot gases, and winds of more than 1,000 miles per hour scourged the planet. The Earth darkened under a dust cloud of airborne debris, causing massive extinctions of plants and animals. Fungi inherited the Earth, surging to recycle the post-cataclysmic debris fields. The era of dinosaurs began, and then ended 185 million years later, when another meteorite hit, causing a second massive extinction. Once again, fungi surged, and many symbiotically partnered with plants for survival. The classic cap and stem mushrooms, so common today, are the descendants of varieties that predated the second catastrophic event. The oldest known mushroom, encased in amber and collected in New Jersey, dates from Cretaceous time, 92 to 94 million years ago. Mushrooms evolved their basic forms well before the most distant mammal ancestors of humans. Mycelium steers the course of ecosystems by favoring successions of species. Ultimately, mycelium prepares its immediate environment for its benefit by growing ecosystems that fuel its food chains. Ecotheorist James Lovelock, together with Lynn Margulis, came up with the Gaia hypothesis, which postulated that the planet's biosphere intelligently piloted its course to sustain and breed new life. I see mycelium as the living network that manifests the natural intelligence imagined by the Gaia theorists. The mycelium is an exposed sentient membrane, aware and responsive to changes in its environment. As hikers, deer, or insects walk across these sensitive filamentous nets, they leave impressions, and mycelia sense and respond to these movements. A complex and resourceful structure for sharing information, mycelium can adapt and evolve through the ever-changing forces of nature. I especially feel that this is true upon entering a forest after a rainfall, when I believe interlacing mycelial membranes awaken. These sensitive mycelial membranes act as a collective fungal consciousness. As mycelia's metabolism surge, they emit attractants, imparting sweet fragrances to the forest and connecting ecosystems and their species with scent trails. Like a matrix, a biomolecular superhighway, the mycelium is in constant dialogue with its environment, reacting to and governing the flow of essential nutrients cycling through the food chain. I believe that the mycelium operates at a level of complexity that exceeds the computational powers of our most advanced supercomputers. I see the mycelium as the Earth's natural internet, a consciousness with which we may be able to communicate. Through cross-species interfacing, we might one day exchange information with descendant cellular networks. Because these externalized neurological nets sense any impression upon them, from footsteps to falling tree branches, they could relay enormous amounts of data regarding the movements of all organisms through the landscape. A new bioengineering science could be born, dedicated to programming myconeurological networks to monitor and respond to threats to environments. Mycelial webs could be used as information platforms for mycoengineered ecosystems. The idea that a cellular organism can demonstrate intelligence might seem radical, if not for work by researchers like Toshiyuki Nakagaki. He placed a maze over a petri dish filled with the nutrient agar and introduced nutritious oat flakes at an entrance and exit. He then inoculated the entrance with a culture of slime mold, Physarum polycephalum, under sterile conditions. As it grew through the maze, it consistently chose the shortest route to the oat flakes at the end, rejecting dead ends and empty exits, demonstrating a form of intelligence, according to Nakagami and his fellow researchers. If this is true, then the neural nets of microbes and mycelia may be deeply intelligent. A few recent studies support this novel perspective that fungi can be intelligent and may have the potential as our allies, perhaps being programmed to collect environmental data, as suggested above, or to communicate with silicon chips in a computer interface. Envisioning fungi and nanoconductors in microcomputers, Gorman and his fellow researchers in Northwestern University have manipulated mycelia of Aspergillus niger to organize gold into its DNA. Its effect creating mycelial conductors of electrical potentials. NASA reports that microbiologists at the University of Tennessee, led by Gary Saylor, have developed a rugged biological computer chip housing bacteria that glow upon sensing pollutants, from heavy metals to PCBs. Such innovations hint at new microbiotechnologies on the near horizon. Working together, fungal networks and environmentally responsive bacteria could provide us with data about pH, detect nutrients and toxic waste, and even measure biological populations. Fungi in outer space? Fungi may not be unique to Earth. Scientists theorize that life is spread throughout the cosmos and that it is likely to exist wherever water is found in a liquid state. Recently, scientists detected a distant planet 5,600 light-years away, which formed 13 billion years ago, old enough that life could have evolved there and become extinct several times over. It took 4 billion years for life on Earth to evolve. Thus far, 120 planets outside our solar system have been discovered, and more are being discovered every few months. Astrobiologists believe that the precursors of DNA, pre-nucleic acids, are forming throughout the cosmos as an inevitable consequence of matter as it organizes, and I have little doubt that we will eventually survey planets for mycological communities. The fact that NASA has established an astrobiology institute and that Cambridge University Press has established the International Journal for Astrobiology, that's strong enough support for the theory that life springs from matter and is likely widely distributed throughout the galaxies. I predict an interplanetary journal of astromycology will emerge as fungi are discovered on other planets. It is possible that protogermplasm could travel throughout the galactic expanses, riding upon comets or carried by stellar winds. This form of interstellar protobiological migration, known as panspermia, does not sound as far-fetched today as it did when first proposed by Sir Fred Doyle and Chandra Wickramasinghe in the early 1970s. NASA considered the possibility of using fungi for interplanetary colonization. Now that we have landed rovers on Mars, NASA takes seriously the unknown consequences that our microbes will have on seeding other planets. Spores have no borders. The mycelial archetype. Nature tends to build on its successes. The mycelial archetype can be seen throughout the universe, in the patterns of hurricanes, dark matter, and the internet. The similarity in form to mycelium may not be merely a coincidence. Biological systems are influenced by the laws of physics, and it may be that mycelium exploits the natural momentum of matter, just like salmon take advantage of the tides. The architecture of mycelium resembles patterns predicted in string theory, and astrophysicists theorize that the most energy-conserving forms in the universe will be organized as threads of matter energy. The arrangement of these strings resembles the architecture of mycelium. When the internet was designed, its web-like structure maximized the pooling of data and computational power while minimizing critical points upon which the system is dependent. I believe that the structure of the internet is simply an archetypal form, the inevitable consequence of a previously proven evolutionary model, which is also seen in the human brain. Diagrams of computer networks bear resemblance to both mycelium and neurological arrays in the mammalian brain. Our understanding of information networks in their many forms will lead to a quantum leap in human occupational power. Mycelium in the web of life. As an evolutionary strategy, mycelial architecture is amazing. One cell wall thick, in direct contact with myriad of hostile organisms, and yet so pervasive that a single cubic inch of topsoil contains enough fungal cells to stretch more than 8 miles if placed end to end. I calculate that every footstep I take impacts more than 300 miles of mycelium. These fungal fabrics run through the top few inches of virtually all land masses that support life, sharing the soil with legions of other organisms. If you were a tiny organism in a forest soil, you would be enmeshed in the carnival of activity, with mycelium constantly moving through subterranean landscapes like cellular waves, through dancing bacteria and swimming protozoa, with nematodes racing like whales through a microcosm of sea life. Year-round, fungi decompose and recycle plant debris, filter microbes and sediments from runoff, and restore soil. In the end, life-sustaining soil is created from debris, particularly dead wood. We are now entering a time when mycofilters of select mushroom species can be constructed to destroy toxic waste and prevent disease, such as infection from coliform or staph bacteria and protozoa and plagues caused by disease-carrying organisms. In the near future, we can orchestrate selected mushroom species to manage species successions. While mycelium nourishes plants, mushrooms themselves are nourishment for worms, insects, mammals, bacteria, and other parasitic fungi. I believe that the occurrence and decomposition of a mushroom predetermines the nature and composition of downstream populations in its habitat niche. Wherever a catastrophe creates a field of debris, whether from downed trees or an oil spill, many fungi respond with waves of mycelium. This adaptive ability reflects the deep-rooted ancestry and diversity of fungi, resulting in the evolution of a whole kingdom populated with between 1 and 2 million species. Fungi outnumber plants in a ratio of at least 6 to 1. About 10% of fungi are what we call mushrooms, and only about 10% of the mushroom species have been identified, meaning that our taxonomic knowledge of mushrooms is exceeded by our ignorance by at least one order of magnitude. The surprising diversity of fungi speaks to the complexity needed for a healthy environment. What has become increasingly clear to mycologists is that protecting the health of the environment is directly related to our understanding of the roles of its complex fungal populations. Our bodies and our environs are habitats with immune systems. Fungi are a common bridge between the two. All habitats depend directly on these fungal allies, without which the life support systems of the earth would soon collapse. Mycelial networks hold soils together and aerate them. Fungal enzymes, acids, and antibiotics dramatically affect the condition and structure of soils. In the wake of catastrophes, fungal diversity helps restore devastated habitats. Evolutionary trends generally lead to increased biodiversity. However, due to human activities, we are losing many species before we can even identify them. In effect, as we lose species, we are experiencing devolution, turning back the clock on biodiversity, which is a slippery slope towards massive ecological collapse. The interconnectedness of life is an obvious truth, and we ignore at our peril. Side note, anyone using the term devolution is assuming that evolution denotes something positive or progressive, when it really doesn't. Evolution, which covers both negative and positive, simply means change. Or so that's what I learned in anthropology. But moving on. In the 1960s, the concept of better living through chemistry became the ideal as plastics, alloys, pesticides, fungicides, and petrochemicals were born into the laboratory. When these synthetics were released into nature, they often had a dramatic and initially desirable effect on their targets. However, events in the past few decades have shown that many of these inventions were in fact bitter fruits of science, levying a heavy toll on the biosphere. We have now learned that we must tread softly on the web of life, or else it will unravel beneath us. Toxic fungicides like methyl bromide, once touted, not only harm targeted species but also non-targeted organisms and their food chains and threaten the ozone layer. Toxic insecticides often confer a temporary solution until tolerance is achieved. When the natural benefits of fungi have been repressed, the perceived need for artificial fertilizers increases, creating a cycle of chemical dependence, ultimately eroding sustainability. However, we can create mycological sustainable environments by introducing plant-partnering fungi, mycorrhizal and endophytic, in combination with mulching and saprophytic mushroom mycelia. The results of these fungal activities include healthy soil, biodynamic communities, and endless cycles of renewal. With every cycle, soil depth increases and the capacity for biodiversity is enhanced. Living in harmony with our natural environment is the key to our health as individuals and as a species. We are a reflection of the environment that has given us birth. Wantonly destroying our life support ecosystems is tantamount to suicide. Enlisting fungi as allies,
we can offset the environmental damage inflicted by humans by accelerating organic decomposition of the massive fields of debris we create, through everything from clear-cutting forests to constructing cities. Our relatively sudden rise as a destructive species is stressing the fungal recycling systems of nature. The cascade of toxins and debris generated by humans destabilizes nutrient return cycles, causing crop failure, global warming, climate change, and in a worst-case scenario, quickening the pace towards eco-catastrophes of our own making. As ecological disruptors, humans challenge the immune systems of our environment beyond their limits. The rule of nature is that when a species exceeds the carrying capacity of its host environment, its food chains collapse and diseases emerge to devastate the population of the threatening organism. I believe we can come into balance with nature using mycelium to regulate the flow of nutrients. The age of mycological medicine is upon us. Now is the time to ensure the future of our planet and our species by partnering or running with mycelium.